Now let's come to how we implement sequential logic, or what are the resources in FPGA which are used to implement sequential logic. So obviously we cannot implement sequential logic with truth tables or lookup tables. So the possible solution is to add a flip-flop to the output of a lookup table like this one. Okay, so if it is a 3x1 LUT, you can have one flip-flop, and if it is a 3x2 LUT, so this is 3x2, you can have two flip-flops connected to every output. Okay. If we have an 8-bit register and we want to implement it on our logic that we discussed, imagine that we have 4 lookup tables here, and each lookup table is a 3x2 lookup table, and we have a flip-flop at the output of every lookup table. So in this case, for example, our x0 and x1 may be mapped here, x2, x3 here, x4, x5 here, x6, x7 here. Similarly, our outputs can be taken from here. Okay, what is the problem? The problem is we need to put the function inside the lookup tables. So what can we put inside the lookup tables? Because all I need is a register. So a register is a combination of flip-flops. I don't need the lookup tables in between. But the problem is that the flip-flops are attached to the output of lookup table. So I am needing these inputs. Okay, so what I can do something like this, that I want to use the LUT as a pass-through. So this is called pass-through LUT. Okay, pass-through LUT means it is used as a kind of pass logic, or it just implement a simple wire. Okay, so how we can find the functionality of this? So this is our unused input. This is x1, this is x0. Remember that the order of variables is important. So this order is very important. If x0 is the most significant bit, it would be different. In this case, x0 is the least significant bit. But I am saying if x0 is on the other side, on the left side, most significant bit, then this functionality at the output would change. So imagine that x1 is connected to y1. So whenever x1 is 0, y1 should be 0. When x1 is 1, y1 should be 1. So you can see this from here. Whenever x1 is 0, you see y is 0, y is 0, y1, 0, 0, 1, 1. Same goes for y0. So we just need to put these values in our 3x2 lookup table, and our LUT will be configured in a pass-through mode. But the question is, isn't it a waste of LUTs? Because we are using LUTs as pass-through. So isn't it a waste? The answer is yes. But fortunately, most of the practical circuits are implemented in what is called pipelining or pipeline fashion. So here is an example of a pipeline adder. So imagine that I have A, B, C and D as input, and I want to add them. Now I can add A and B, and I can store, let's say, the result of A and B. Let me call this sum AB. So I store the sum AB in a register. Similarly, I store sum CD in the register. Then I add sum AB and sum CD, and I get the final sum from here. So you see that there is this level of registers and this level of registers that is between the combinational logic. So the combinational logic is between these register layers, and this kind of RTL model is directly translated to our FPGA architecture. So this FPGA architecture is designed keeping in mind how the actual circuits are structured. So we always have some combinational logic, and then we have these flip-flops. So it's not that bad. Okay. Okay, but we have another solution also. Most of the state-of-the-art FPGAs, they have a sort of configurable connection to the flip-flop. So if you want, you can add a flip-flop to the output of your lookup table. If you do not want, you can bypass it. And how it is achieved is by designing a configurable logic block, or CLB. You already heard this name in the this lecture. So let's see what is the advantage of CLB. So it is basically the basic functional unit of FPGA. How to make a flip-flop optional is something like this. Imagine this is our CLB box, and this CLB box contains at the moment a 3x1 lookup table, and we have a flip-flop that is connected to the output of this lookup table. But also we have here a 2x1 mux. So if a user wants, he can use the flip-flop and select the version that is coming from the flip-flop. And if the user want to bypass the flip-flop, he can bypass the flip-flop by selecting the appropriate mux input. The problem with the flip-flop is that if the user takes the output from the flip-flop, it will be delayed by 1 cycle. So remember that flip-flop adds a unit delay. Okay, so a flip-flop adds a unit delay. If you put two flip-flops together after one another, such that the output of one is the input of the other, then you will have 2 unit delays. Okay, so a configurable logic block contains more than one lookup table. So this is 1 unit. Okay, this is now a 3x2 lookup table, and this is another 3x2 lookup table, and each one has this bypass mux for let me call this flip-flop bypass mux. So each one has these flip-flop bypass muxes, and additionally you see another mux here. This mux is also very interesting, and the reason is that you see this red line. This is basically a connection from one of the output line of the flip-flop, so this of the lookup table on the right side, to the lookup table on the left side. So what is the advantage of this red line? The advantage is it provides an efficient way of handling common I/O between adjacent LUTs. This reason is for the why we want to have multiple LUTs inside a CLB. The reason is if we put multiple lookup tables in a CLB, they can share the input output line. These lines, they can be shared. Okay, so which means the routing resources can be saved. The second reason is this one, this red line, that this line is sort of non reconfigurable, and it is very close from the lookup table on the right side to the lookup table on the left side. So in the coming slide we will see there are two kinds of wires. One is local and then the other are global. The local wires, for example this red one in this case, they are very fast. Okay, so if you have for example ripple carry adder, okay, you are aware of ripple carry adder, you have learned about this in your DLD course and also in your VLSI course. So a ripple carry adder is characterized by this chain of carry propagation. So imagine if you have ripple carry adder like this, that this is the first full adder and this is the second full adder, and this is our C out from flip-flop 1, which is input to flip-flop full adder 2. So in this case the full adder 1 is mapped here, so this is our full adder 1 and this is our full adder 2, and every full adder has a sum output and a carry output, and you see the carry output is directly mapped to this red line. Okay, so it is you remember that the reason for ripple carry adder to be the slowest is basically this carry line. Okay, this carry line, and why it makes it the slowest, because flip-flop 2 has to wait for full adder 2 has to wait for full adder 1 to complete its addition. Okay, so that makes it very slow, and the propagation delay of ripple carry adder becomes worse if the number of bits increases. Okay, so this kind of local connection between lookup tables can make it very fast. So configurable logic block have specialized connections between adjacent CLBs. So imagine that your FPGA is something like this. It is like a sea of CLBs. So this is CLB 1, 2, 3, 4. So your FPGA can be considered like a sea of CLBs, and these CLBs has specialized connections. So there are specialized connections to connect the CLB to adjacent CLB. So for example, this is 1 and 2 are adjacent, and 1 and 3 are adjacent. So there are specialized connections which can improve the speed of certain application. For example, the carry propagation in ripple carry adder. Okay, some commercial CLBs are more complex than the simple one that we discussed. It has other stuff which I will not go into detail here, but if you want you can check the documents of, for example, 7 series CLB. You can check, search this, and you will find a whole document about the architecture of 7 series FPGAs and how many lookup tables are there and how the flip-flops are connected, and all those things. And this changes from FPGA to FPGA. So for example, if we talk about vertex 4 FPGA, each CLB has what is called slice. So one CLB has two slices. This is our CLB. It has two slices. One slice was called odd, the other slice was called even, and this slice contains two LUTs. This slice contains two LUTs. Okay, but this was vertex 4. Now in 7 series FPGAs, for example Arctic 7 or Kintic 7, this has increased from 2 to 4 LUTs per slice. Okay, so it differs from company to company and from FPGA family to FPGA family. So these are some examples. If you want to check the architectures of different CLBs, so you can follow these links. Okay, so what's else is inside the configurable logic block? A configurable logic block can implement any combinational plus sequential logic, and all circuit consist of combinational and sequential logic. So you would think that CLB is all what is needed in an FPGA, but this is not true, because the most important element is the interconnect, or how we connect one CLB to other CLB, and this is very important part of an FPGA. Sometimes this is called the routing architecture. So FPGAs need some way of connecting CLBs together, and this is this kind of interconnection has to be reconfigurable. Okay, so imagine that I want to connect CLB1 to CLB100. So the architecture should be reconfigurable in a way that I should be able to connect CLB1 to CLB100. Okay, so this kind of flexibility should be there. The problem is how to make the connections reconfigurable, because you know that we used to connect two things together with wires, and wires are not reconfigurable. So how can we design a routing architecture which is reconfigurable and which enables me to connect any two CLBs in this sea of CLBs together? So let's dive into some of the specifics. If the FPGA doesn't know which CLBs will be connected, where to put the wires, okay, so the only solution is to put the wire everywhere. So you see there is this line, horizontal running line, okay, then there are vertical running lines. Okay, so CLBs are typically arranged in a grid, in a two-dimensional grid, with wires all around. In every direction there are wires that are passing here and there. Now the problem is how to connect CLB to a wire. Okay, so we have wires on the left, we have wires on the right, we have wires on the top, we have wires on the bottom. How to connect the wires together? The answer is we connect them through something that is called connection box. So a connection box is a device that allows inputs and outputs of CLB to connect to different wires. Okay, so for example, let's say CLB1 wants to connect to CLB2. The output of CLB1 can be connected to the output of CLB2 through, for example, this connection that I have drawn. Okay, so let's see what is inside the connection box. So the connection box are characterized by the flexibility, and how we define flexibility is the number of wires a CLB input / output can connect to. So for example, in this case the flexibility is 2, because a single wire can connect to these two wires. Similarly, a single wire can connect to these two wires. Similarly, this line can connect to these two, and similarly, so here we say the flexibility is 2. In this one we have 3, so each wire can connect to 3, so the flexibility is 3. And note that the dots represent possible connections. These dots are for example your pass transistors from VLSI course, and you can or they can be the other transistor, normal transistors. So if you apply a 0 to them, it may be closed. If you apply a 1 to them, it may be open, okay, depending on which kind of PMOS or NMOS you are using. So connection box has then different kinds of topologies. For example, define the specific wires each CLB/IO can connect to. For example, here you see the topology is like this, that you can connect to 2 close wires, but in this case the topology is that you can connect here or here, okay. So these are 2 different topologies. So here the flexibility is same. The flexibility is 2 here and 2 here, but the topology is different. In one case you can connect to adjacent wires, and in the other case you can connect to alternative wires. Connection boxes allow CLBs to connect to routing wires. So these wires, they are called routing wires. All these horizontal and vertical wires are called routing wires, but it only allows us to move signals along a single wire. So okay, so for example, what this means is that I can connect to this wire, and this wire runs from top to bottom, okay, but I am on the same wire. What if I want to connect to multiple wires? How do FPGA connect wires together? So that is the problem number 4. So the solution is what is called a switch box. You see this yellow square in the middle of these 4 CLBs. So these are connection boxes or CBs, and this is our switch box or SB. Now a switch box is interesting because it can connect horizontal and vertical channels. So all the horizontal and vertical routing wires can be connected. So you can change the direction from horizontal to vertical or from vertical to horizontal. Again, we need to characterize the switch boxes. So a switch box has a parameter called flexibility, where flexibility defines how many wires a single wire can connect to. Okay, if it can connect to 2 wires, we say the flexibility is 2. Topology defines which wires can be connected. So a planar / subset switch box only connect tracks with same ID / offset. For example, this is a planar switch box, not a connection box. We are talking about switch box. So it can connect only 0 to 0. Okay, so this is 0 and this is 0. It can connect only 1 to 1. Okay, it can connect only 2 to 2. So this is a planar switch box. And then we have a Wilton switch box. So a Wilton switch box connects tracks with different offsets. So for example, it can connect 0 to 1 or 1 to 0 or 2 to 1 or 1 to 2 or 2 to 3. So there are different, this is different topology than the planar topology. Okay, so a lot of complexity and a lot of design decisions go into this, how we design the switch box. And if you have taken a course on computer networking, this is somehow computer used to route packets. So you need a sort of computer network architecture, and those architectures have to be efficient for the propagation of packets. So this kind of switch box also have to be very efficient in terms of supporting the connections that are required in an FPGA architecture. So why do flexibility and topology matter? So why does the flexibility and topology matter? The most important result of these parameter is basically what is called routability, and it is a measure of number of circuits that can be routed. For example, let's imagine these two figures. The source is here at the output of, for example, CLB1, and it is connected with the red lines here, and this is our destination. Okay, this is fine, but let's say if our destination is not the third wire but the fourth wire, then there is practically no way to route it, because from this I can either connect to this or this, and in any case I can only come here or I can only come here. I cannot reach this destination. So you see, this planar switch is not very useful, and or in other words, the routability is not better. Okay, so this is the main design problem for switch boxes. You want switch boxes in such a topology and with such flexibility that you are able to route maximum circuits. Okay, switch boxes, short channel useful for connecting adjacent CLBs, and long channel useful for connecting CLBs that are at large distances. So these are the two kinds of switch boxes. For example, here we can use short channel switch boxes, and here we can use long channel switch boxes. Okay, here is another picture that shows how the switch matrix is connected to our CLB. So you can say here is our part of routing architecture. Okay, this we talked about when we were discussing the structure of lookup table, but this part is our routing part. So you can see that you can connect these wires depending on these SRAM cells. Either this wire can connect to the input of lookup table, or this wire can connect, or that wire can connect, and this is basically the switch matrix multiplexer. It is a part of you can say the connection box or the switch box, and usually these multiplexers are implemented in pass transistor logic. So you can convince yourself that this is a multiplexer. Okay, and this is another picture which shows some details. Again, the whole FPGA fabric is these switch boxes, and they are connected to the CLBs or the lookup tables. Here is one example of the input output element, which we have not went into details till now, but obviously at the boundaries of the FPGA you have these pins which enables you to connect to the outside world. So those pins are called IOB, or input output blocks. Okay, maybe we come to it in the future slides. So an FPGA fabric is CLBs plus these routing, and on the edges or boundaries we have the IOB blocks. Now imagine if I want to implement a memory on FPGA. How can I implement a memory? I can use flip-flops in the CLBs to create memory, but this will be a very poor choice of resource to use for memory. For example, if I want to create a 1 megabyte of memory. Okay, so the problem was to design a 1 megabyte memory, and you have to use a configurable logic block that has a single lookup table which has 3 inputs and 2 outputs. So it is something like this. This is our CLB, which has 3 inputs and it has 2 outputs, and every CLB has this flip-flop. Every output has this flip-flop connected to the output. So this is our CLB, and if we want to implement 1 megabyte of memory using this CLB, we can support only 2 bits per CLB. Okay, then we would require, in order to implement 1 megabyte of memory, 1 megabyte is equal to 1 megabyte multiplied by 8 bits per byte and divided by 2 bits per CLB, which gives us 4 million CLBs. Okay, so you see that this is an exponential growth in the number of CLBs. So the result is that we do not implement memory using CLBs. It is very inefficient to implement memories using CLBs. So how we do it? We do it with 2 solutions. The first solution is to use lookup tables for memory, and I talked about this in the previous slides. This was called LUT-RAM or distributed RAM. This is one solution, that instead of using flip-flops, you can use LUT-RAMs to synthesize your memory. The second option is what is called block RAM or BRAM. Okay, so this is the second option which you can use to synthesize your memory. And if we talk about Xilinx architecture, they provide BRAMs with different kinds of features. So for example, you can use a single or dual port block RAMs. You can also use the block RAM as FIFO. So FIFO is first in first out memory, and we talked about this in the VLSI course. Okay, so then the FPGA architecture can be redrawn as in this figure. You see now we have the columns for BRAMs here. So along with CLBs and switch boxes and connection boxes, we have now block RAMs embedded inside our architectures. So we have different columns in our fabric. Then another component that is found in state-of-the-art FPGAs is DSP blocks. These DSP blocks are very suitable to implement MAX. MAX stands for multiply and accumulate. And this is one of the basic building operations that is found in many DSP algorithms. For example, convolution is a MAC operation. So FPGA designers have realized this the importance of MAC operations, and instead of synthesizing or building the MAC unit with CLBs, they gives you this built-in DSP processors. So you have the small DSP processors on your FPGAs, okay, and these DSP processor can implement a lot of DSP operations. For example, MACs, they can implement FIR filters, they can implement square root or different mathematical operations very efficiently. So you see that these modern FPGAs are sort of heterogeneous devices. They are not homogeneous. It would be homogeneous if we only had CLBs, but along with CLBs we have these small DSP processors which are called DSP48, and we have block RAMs, and we have so many different kinds of resources. We covered some of them in this lecture. If you want to study the full detail, you can go to the FPGA user guides. So there are so many different kinds of resources for different operations. For example, there are resources for high speed input output. Gigabit transceivers are there. There are clock resources there. There are internal configuration access ports and so many other things. This slide shows the sort of actual image from Xilinx 7 series FPGA, and you see these colored different colors of columns, and these columns represents different resources. So for example, on the boundaries we have select IO and CMT, which stands for clock management resources. You have DSP columns, you have serial transceivers, you have PCI Express, you have block RAM columns. So these days FPGAs are truly heterogeneous, and maybe we talk about this. Nowadays there are complete processors that resides on one side of the FPGA fabric. For example, the Zinc SoC stands for System on Chip. It has dual core Cortex A9 processor on one side, and this was introduced in, I think, late 2012. If we talk about today's offerings from Xilinx, we have I think quad core processors, we have even GPUs, we have the real-time processors or microcontrollers. They all are integrated on the same chip, okay? So you can say that these different kinds of resources are there to support different algorithms. So for example, if you want to connect to a user interface, then a processor is the best choice. But if you want to implement for example image processing algorithm, maybe GPU or FPGA is a better option, okay? So because of the different kinds of applications that a user can map onto these platforms have really grown into heterogeneous devices that no one imagined maybe a decade or a decade and a half ago. Okay, so with this I close this part of the lecture, and we will continue with the configuration layer of FPGA in the next part.